Good morning, student. Today we are going to learn quadrature phase shift keying. After the completion of today's session, you are able to define quadrature phase shift keying and explain operation of transmitter and receiver of quadrature phase shift keying. So, in communication systems, we have two main resources. These are the transmission power and the channel bandwidth. The channel bandwidth depends upon the bit rate. If two or more bits are combined in some symbols, then the bit rate will be reduced. This reduces the transmission channel bandwidth. In quadrature phase shift keying, two successive bits in the data sequence are grouped together. Means in QPSK, which is a form of PSK, phase shift keying, two bits are modulated at once. It selects one of four possible carrier phase shift, that is 0 degree, 90 degree, 180 degree and 270 degree. Okay. So, in case of BPSK, binary phase shift keying, when symbol changes the level, the phase of the carrier is changed by 180 degree. Okay. In BPSK, when symbol changes the level, the phase of the carrier is changed by 180 degree. Because there were only two symbols in BPSK, that is 0 or 1. However, in QPSK, two successive bits are combined, means two bits are grouped. Okay, this combination of two bits forms four distinct symbols. As we know, if two bits are given, then 2 to the power n, that is four combinations are, that is 0 0 0 1 1 0 1 1. Okay, so when the symbol is changed to next symbol, then the phase of the carrier is changed by 90 degree. So here between two input combination, the phase shift is difference is 90 degree. So 0 plus 90, 90 degree, 90 plus 90, 180 degree, 180 plus 90, 270 degree. Okay. So if we draw a diagram, then it is like this. Means this one is the 0 0. Then when 0 1 comes, here 90 degree phase shift occur. Then when 1 0 input given, then again 90 degree phase shift occur. Then when 1 1 given in the input, again 90 degree phase shift occur. Okay, this one is the diagram. This one is the carrier signal and this one is the modulated signal. So when 0 0 is given in the input, then at the output we get the signal with 0 degree phase shift. Here you can see it is written that at 0 0 input combination, the phase shift is 0 degree. Then when 1 0 is given, 1 0, this one, when 1 0 is given, then the phase shift is 180 degree. See here, if this one is the diagram 0 0 0 1 1 0 1 1, so the graph is like this. When 180 degree phase shift means this line, here the phase changes 1 0. So because of that, here the waveform changes its phase here. Then when 0 1 is given, 0 1 means this point, means the waveform start from this. So see here, the waveform starts from this point, okay. Then when 1 1 is given, this one is the 1 1 point, so from this point the waveform will start. So here it is also shown that waveform will start from this line. So as per the input combination given, the phase shift occur accordingly, okay. Then this one is the QPSK transmitter. So in QPSK transmitter, first the input binary bit given to the bipolar energized encoder. We earlier discussed about this, that when a unipolar signal is given to the bipolar encoder, then at the output we get the signal having two polarities, that is plus and minus. After that it is given to the demultiplexer. Here the demultiplexer used as a bit splitter, okay. Let's see, when a input given as 0 1 1 0 1 1, let serial it or number it 1 2 3 2 3 4 5 6. So here the odd numbers are 1 3 5. So the demultiplexer split the input signal into two waveforms. One is even, other one is odd. So as per the numbering, 1 3 5 bits are odd bits. So here the signal is taken having odd bits, and the other 2 4 6 bits are even bits. So these input signals are given to this side 1 0 1, okay. Like this the waveform is separated accordingly, even bits and odd bits. Then these even bits are denoted as B E of t, and these odd bits are denoted as B O of t. Then these signals are multiplied with the carrier signal that is given here, okay, here to the input of the multiplier. So the input to the multiplier, that is B E of t and root PS cos omega ct are multiplied. Like this, in the second multiplier two inputs are given, that is B O of t and root PS sin omega ct, that are also multiplied. So at the output of the multiplier we get B E of t into root PS cos omega ct, and here also root PS sin omega ct into B O of t we get. And at the output finally we add both the signals, and at the output we get S of t equal to B E of t root PS cos omega ct plus B O of t root PS sin omega ct. This one is the final equation, that is QPSK signal, that is transmitted from the transmitter side, okay. Next is the QPSK receiver. So let us represent the received QPSK signal by S of t, okay. So the received QPSK signal S of t is raised to fourth power, that is S to the power 4 of t, okay. By using this block, raised input to fourth power, the S of t also raised to fourth power. Then this signal is filtered by using a band pass filter, okay. This one is the band pass filter with a center frequency of 4 omega ct. Because of that, here we get cos 4 2 pi fct. Then the output of band pass filter applied to the frequency divider, which divides the frequency at the filter output by 4. Here means the output of the filter divided by 4 generates the two carrier signal, that is sin omega ct and cos omega ct. The incoming signal S of t is applied to two synchronous demodulators consisting of a multiplier followed by an integrator. So this received signal is applied to applied directly to the multiplier followed by integrator. These are the synchronous demodulators. Okay, each integrator integrates over a 2-bit interval of duration, that is 2 TB. Here limits are given. See here, 2k minus 1 into TB, then 2k plus 1 into TB. So when k equal to 0, then the upper limit is TB and the lower limit is minus 1 TB. Okay, so like this we can see the duration 2-bit interval of duration is 2 TB for each case, that is k equal to 0, k equal to 1, k equal to 2, for any case. Okay, one synchronous demodulator uses cos omega ct as a carrier signal and the other one uses sin omega ct as a carrier signal. Let's see the derivation. First we discuss about the upper integrator. So the input to the upper integrator, that is S of t, that directly given to the multiplier, and the carrier signal. See here, the upper, this one is the multiplier. To this multiplier, here S of t is given and sin omega ct is given. So at the output of the multiplier we get S of t into sin omega ct. So the input to the multiplier is S of t sin omega ct, and the equation of S of t we already discussed, that is B, here see, B e of t root ps cos omega ct plus B0 of t root ps sin omega ct. With this a sin omega ct is multiplied. So see here, B0 of ps sin omega ct into sin omega ct, so sin square omega ct, then Be of t root ps cos omega ct into sin omega ct. So after that the input given to the integrator is integrated. Here it is integrated over 2-bit period. Then we substitute the value of S of t into sin omega ct. This one is the equation. Then here you can see sin square omega ct. Using mathematical formula we solve this equation. As we know, sin square omega ct equal to 1 minus cos 2 omega ct by 2. So here we put the value, here 1 by 2, then here 1 minus cos 2 omega ct. Next, in this term, here we can see sin omega ct into cos omega ct. Here also we use another mathematical formula. So sin omega ct into cos omega ct equal to 1 by 2 sin 2 omega ct. So here is the 1 by 2 and here is the sin 2 omega ct. After integration, here we get the final value, that is half b0 of t root ps bracket start 2k plus 1 whole into tb minus 2k minus 1 whole into tb. After that we just open up these terms, so here it is 2k tb plus tb minus 2k tb plus tb. So 2k tb cancelled out, then here is the final equation, that is 1 by 2 b0 of t root ps tb. See here, this one is the 2 tb. Okay, so 2 cancel out. At the output we get b0 of t root ps tb. Okay, similarly we can prove that the output of the lower integrator is also b e of t root ps tb. Okay, so this one is the diagram. Thus at the output of the two integrators we obtain the bit stream b0 of t and be of t. This one is the b0 of t tb root ps, and this one is the be of t. This one is the be of t. Okay, here it is be of t tb root ps. So at the end of each integration time, for each integrator, the integrator output is sampled. The samples are taken alternately. Here the multiplexer used here like a switch. Okay, so it takes alternately from the two integrator outputs at the end of each bit time tb, and these samples are then held in the latch. Means here there is a latch present. Okay, latch. Latch for the bit time tb. Each individual integrator output is thus sampled at interval of 2 tb. At the output of the latch we get the signal, that is b of t. Okay, so this is all about QPSK. Thank you.